Here we are faced with a word problem about the number of bacteria in a sample at some time. Some stuff. Maybe you want to go into mathematical biology, which is an actual field. You'll deal with a lot of problems like this. So they deal with differential equations. So what we have here is a differential equation. But I tell you this beforehand. But if I don't know what the differential equation is and I don't know what's going on, then I would just read the problem and try to see what I'm looking to find. So what is the goal here? Take a moment to think about it, see what we want to find. For me, it is clear. We're looking to find the population at t is equal to 50. Okay, you've been able to locate this goal, but how would you formulate it mathematically? Yes, you would like to find p of the population at t is equal to 50. So you could just say p of 50. Well, to find p of 50, I think you first need to find p of t. Right, you need to have the function so you can plug values inside. I think that's very reasonable. I don't think I'm asking for too much. But then what do we have? Maybe I'll use purple. I don't like green in this case. No, we have enough colors. What do we have? We only have two things. So our givens are p of 0 is equal to 100. I'm not sure how we can use this. At least so far, it's not clear to me. I'm lying, but I don't know. But maybe this is more obvious. So I have the rate of change of p with respect to time is equal to 20 e to the 3t. So if I have the rate of change, how do I find the function? I know that if I have the function, I can differentiate to find the rate of change. So if I want to do the opposite, I would integrate. I hope that's clear. If it's not, you cannot let me know, because if you're watching a video, you can always text me if you have questions. Email me. So we need to integrate this thing. We need to integrate dp by dt. dp by dt is a function of time. So we probably need to integrate this with respect to time. Now, would this give me my p of t? Yes. Yes, it would. Why? Well, it's funny. It's funny, and this is not the way you should do it. So I'm warning you, this is not why it works. Okay, this is not why it works. But if you take algebraic action on the fraction, then you get, you're integrating dp, and the integral of dp is just p, right? So don't do this, this is like in quotations. Whatever is in quotations is just a disclaimer. It doesn't really work like that. So there is some mathematics involved. I don't want to discuss it here. But this is, roughly what happens. But okay, so I need to integrate this dp by dt. This should not be a difficult task, and I don't believe this is the goal of the exercise, but nevertheless we can discuss the integral. And I would like to do so by thinking of the function whose derivative is this. Maybe I would isolate the 20 so that I can focus purely on e to the 3t. So the derivative of what gives us e to the 3t? It's a good question to ask. Well, the derivative of e to the 3t itself is what? It should be e to the 3t, because you know it's a derivative of e to the x is e to the x. But don't forget to multiply by the derivative of the inside function. The inside function is 3t and the derivative of it is 3. So this is the derivative. Okay, then probably with each derivative I'm multiplying by 3. So in this case I would multiply by 3 to get 1. Then I probably had 1/3 in the first place. This is what I mean. So this is to account for the derivative. Now what's going on here? It's just a chain rule, or maybe you could say anti-chain rule. Yeah, so there should be a g prime here. So this is what the chain rule tells you. You can verify this yourself. So I would like you to verify that the derivative of this thing is that thing. Now importantly, do not forget the constant of integration. So this is important. So please verify that the derivative of this thing is that thing. But I want you to notice now that if we equate this to p, oops, okay, this is the answer. You should not see this. I clicked by accident. I mean, if you want to see the answer, you can just, move until the very end and you'll find it. So I think it's fine. Or you can just look at the answers. I think the answers are displayed after the sheet is due. Anyway, so we would equate this to p of t, but then it's a problem because c can be anything, right? C is any constant, and if c is any constant, then if you think about this for a moment, the output can be anything, because no matter what this first thing is, I can just adjust this other constant, because I have a degree of freedom to give me any result I want. So let's say I get this to be -5 and I want to get 0, so I've just set this to be equal to 5. So what I want to say, we get an infinite class of functions which are candidates to be our population. But here there is a trick which we can use. We don't have infinitely many functions, there's only just one function. And you would notice this by looking at the givens which you still have not used. So this given we've used, that's why I checked it. But maybe I crossed it, I didn't check it. So what have I not used yet? The answer is clearly this. So I've not used this yet. So if this is true, and I would like to use this part, then I would get the following. I'll get that p of 0. On one side, it should be equal to 100. And on the other side, it should be equal to this. But do not forget to plug in for this very specific choice of t, which is 0. To put also here 0. If you put a 0 here, you get 1. So you get that 20 times 1/3 plus 20 times c. I mean, 20 times a constant is just a constant, right? 20 times a constant is just a constant. But I'll be careful here to also indicate this here. Because if I don't, then there's a problem. 20 times a constant is just a constant. So, this is what I have. right? And then this is equal to 100. So in that case, my c would be equal to 100 minus 20 times 1 over 3. So 20 over 3. I can write this, of course, as 300 over 3. You know, if you just do the mathematics behind this, you'll get 280 divided by 3, which is some number. You don't really care about it. But this is good, because now I can write P of t is equal to this. And I have a constant. My constant defines what my function looks like. That's the really cool part. So it's not just any constant, it's the constant 280 divided by 3. This is what we usually call the initial condition. And it is the initial condition in this case because it's at t is equal to 0. So for this initial condition, we define our function. If we don't have an initial condition, then there will always be some sort of problem that arises with infinitely many functions which need to for which you need to determine a starting point. So you do get infinitely many functions, but they differ by a constant. And if you determine the constant using one piece of info like this one, which you will almost always be provided with, then you can say, okay, this is my unique function that satisfies this very specific scenario and this very specific initial condition. Okay, we have our P of t, then computing the final result should not be a difficult task. I just write P of 50 will be 20 over 3 times e to the 3 times 50 plus 280 divided by 3. Yes, I just noticed something. I did not write this in here. It was hiding behind my video footage. So I need to be careful with the boundaries. So this is C, if you have not seen it. Okay, but then this is not too difficult, because now I can summon the answer. It's 9.291 times 10 to 65. So that is approximately, 9.291, that's 9.3 times 10 to 65. That's a very big number. I don't know if you realize how big this is. But this is a very, very, very big. And in this case, in this very specific case, it is the answer for the exercise. And if you think about this, this is a very fast rate of change. So at t is equal to 0, the bacteria is 100. And then after 50 intervals of time, let's say 50 minutes, the bacteria is 9.3 and multiplied by 10 to the 65, which is 65 zeros. So it's 1 with 65 zeros. It's not 65 million, it's not 65 trillion, it's 65 zeros. Like a billion has 9 zeros. This has 65, just to give you perspective. So bacteria grows at a very fast rate. But then that's fine. Not all bacteria is bad. Actually, 99% of bacteria is good, but some bacteria is bad for us. But maybe that's a discussion for a biology class. For now, this is all I wanted to say.